Okay. So, now this as I said is one way by which you can assign probabilities to these Borel sets. A different way of, or a more general way, in fact it turns out, more general way of assigning, another way, right, another more general way of assigning probabilities is through what? Is through, what is this? Those of you that have studied probability before, to give me the answer to this question. What we call a cumulative distribution function, a CDF. And here we will always use uppercase, capital letters to specify the CDF. To specify the acronym will always be in caps. Right. So, what is this CDF? Right. These are, unlike the PDF, the CDF is actually a probability. It is not, right. You do not have to do anything to it. It is like in some sense the counterpart of a PMF, if you will, right. So here we have, let us say, a function in general, the function f. So let me call the CDF as, we will use capital F. So what is the domain of this f? Typically we will, right, define it for the entire real line, and let us say, right, okay, it is a probability, so its range is only the interval 0 to 1. So, and what are the properties of this f, right? Okay, it is going to be a probability, right? Its domain is the entire real line. Basically we want it to be a non-decreasing function of x. F of x is a non-decreasing function. As x increases, this it should not decrease, right, decrease. It is a non-decreasing function of x, right. That is very, very important constraint. Why? Because we will see, but before I look at the exact meaning of f, let me write out two more conditions. I want its limit as x goes to minus infinity. I want, these are requirements, by the way, it is not, right, I want the f to satisfy these. So these are requirements. This, if you want, you can add the word requirements here, right. What do we want this f to look like, right? This should be what value should we assign to this? It should be 0. As x goes to minus infinity, I want f of x to go to 0. Remember, right, by insisting on, if you look at the PDF, if you want the PDF to be integrable all the way from minus infinity to infinity, small f also has to go to 0, but that is not a sufficient condition for right. You know that there are functions which go to 0 which still cannot be integrated, right. As a typical example is 1 by x. So just keep that in mind, but even the PDF has to go to 0. If you right, if it does not go to 0, you cannot it will not have a finite integral, right. But anyway, we are not going to integrate this f right away anyhow. We are just going to put this as a condition, and as x goes to plus infinity, you want this to be 1. In other words, right, the f starts out at 0 at minus infinity and ends up at 1 and plus infinity, and in between what does it do? It does not decrease. So okay, monotonically increases if you want, but it can stay flat also, right. So an example of such an f, let me just make sure I don't, if I want to define something which is for the entire real line, I can define something like this. If somebody were to plot this, what will it look like? what does this look like? Does it satisfy my conditions? Yes, it does. So if I have such an f, then I can say it turns out this probability, this event, that is the portion of the real line from minus infinity to x, I will define it to be, or I will define f of x, I should maybe have put it the other way around, right. F of x, right, at any point is going to be the probability of this event. Now you may ask me, right, what if minus infinity is not part of omega, whatever, right. So obviously this could be a combination of a null event, this interval could be a combination of a null event and a useful portion. But it's, so let me not get into too many not split hairs over the exact, what is, I mean the role of capital omega in this and so on. You can always, it turns out that even when omega is only 0 to 2 pi, you can always look at this, right, this event and meaningful Large probabilities no matter what number you put up here. If you put, for example, any number less than 0, this will become a null event and f of x will be 0. So there is nothing to prevent f of x to be 0 all the way from 0 to minus infinity to 0, for example, because we said it has to be non-decreasing. So you could have something like this. This is one example, this is another example. It can be up to 0, it can be flat, and then it can go to 1 and then remain flat here. This is also possible. Right. In any case, right, if you start out with such a function which behaves like this, then its values can be assigned to be the probability of this event, where we by convention we look at this x as a, we include this the upper limit, the x. This for all x which is not infinity, usually as I said yesterday, we don't usually include the infinity as a closed interval, but anyway for all, but that's we don't have to worry about that in this definition anyhow, right. We can just say for all finite x here, this is a well defined interval and the probability of this interval is given by the value of this function. So why is this more general than this, than the density? It is more general because I can have discontinuities in this f which I cannot get by having a density function. So we'll see that, let's go be a little careful with this, right. So okay, so therefore this is the definition, so which implies then what? That the probability of the interval a to included b, not a but including b, will be what? Will be f of b minus f of a. This follows directly from this, from the definition of the CDF. So this is just by definition, right, given this function, right. In fact, I think I have it right, I am saying that I am starting out with some such function either like this or like this, and then I am saying given this I can always do this, then if I do this, then this follows. The probability of this interval open at this end a, closed at this end b, because this is closed here. So how does this follow from this? Because this is the union of minus infinity to included a and not including a to included b, right, those are disjoint. So that will be f of b, this will be f of a. So again by right basic right, if you take this f of a on this side, it's clear that it has to follow, right. It's this is the union of two disjoint events, as obvious from the construction of this. Okay, all right. What about the probability of the isolated point A itself? This is going to be f of so if I make this be arbitrarily close to A, or okay, So, so supposing I want to I want to include the point A itself. If I just want to look at that point, then all I have to do is look at the value at. So supposing, let me say, if I do something with the jump out here, if I have something like this and a jump and something like this, right? This could also be an f. This could be 1. This could be 0. I have a jump here. Let's say, right? Let's say I have a jump and this is a value. So what I'm saying is this is the value f of A includes, right, the value of the jump at A, if there is a jump. That, pardon me? Yeah, basically I was just going to say that f is defined to be right continuous, right, because we are including this endpoint in the interval. So this difference between, that is f of A minus, which is the limit coming from here, and the value. So this difference is the value, is a probability which comes from this, right? If you make, right, or maybe I should have put B here. Let us say A approaches B. This could have, I mean it's better to have put B here, but doesn't matter, right? Maybe I'm getting confused because I wrote A, and it's probably better to have started B. If it becomes clear if you put B and write this as B minus B minus, isn't it? Instead of writing A, it's okay. Anyway, so I don't want to erase and rewrite, so I'll just leave it as it is. There's nothing wrong with this, right? But this doesn't so directly follow from this, with A, but it follows with B. So what is this saying? This is saying that this model can actually include a combination of points with some finite probability, right, and have smoothly increasing f at other places also, right. It can actually do, the CDF model is capable of being more general than the PDF model. So this, when is this 0? This is 0 if what? If f is continuous at A, right. So this is 0 So at every point where f is continuous, right, you don't have a finite probability of that particular point. But the model allows you to, it says nothing about having jumps in f. It is in fact a countable number of f, right, jumps in f is in fact allowed, right. So let's go back, state that out here. So we can have, or let me say f can have a countable number of jumps, right. And I say that countable can actually be countably infinite. Okay, but supposing your f is small f is the PDF is defined. What is the relationship using calculus between the PDF and the CDF? Supposing f is specified. Then capital F of x is, what is this? In terms of small x, is obviously the integral from minus infinity to x of fu du. Again here we are using the extended domain for small f, and by definition the domain of capital F is the entire real line, right, regardless of the actual portion of the real line that we are interested in. Just conventions that that we are using, that this is the way the CDF is defined and the PDF also. So can this model give you can it ever give you discontinuities in capital F? This cannot, right, the integral can never give you discontinuities unless this f is what, some crazy impulsive type of thing which we are not going to consider in this course, right. Let me also be very clear, in this course we are not going to ever invoke the Dirac impulse, right. So do you agree with me that this capital F is in a way more general, because if you start with this small f, you can always get this capital F using this equation, but the constraint is that this capital F is going to be continuous, which implies that for smooth f turns out to be continuous. So if you start with a smooth, when I say smooth, I mean I am including the case of countable number of jumps, right? No, that is no impulses. So we are not going to, right, consider this case at all, right. So as I said some 10 minutes back, the constraint on small f is that it, right, at best what we will look at in our models will be a continuous a finite number of jumps, and that we will include in our definition of smooth. For example, 0 from minus infinity to 0, and then 1 by 2 pi from 0 to 2 pi, and then 0 afterwards. That is perfectly okay. That is what we call a smooth f, right. So the point is that with such an f, you cannot get any discontinuities f, and that is consistent with our earlier observation that if you use probability, if you define small probabilities based on small f, all individual points will have vanishingly small probabilities. No point can have finite probabilities. However, if you want to, for some reason, as we will see in some homework problems, if you want to have points with some finite probability, more than non-zero, right, you cannot use PDFs. You have to in fact use a CDF to specify that probability distribution, right. So if you want discontinuities like this, jumps like this, you have no choice but to, I mean you can say some textbooks do in fact allow some impulses, but impulses actually it turns out are more, they cause more trouble than they are worth, right. So there are good reasons not to bring them in, right. So we will use PDFs only, right, for continuous CDFs.
So if f has countable number of jumps, then does it mean that the PDF has impulses?
No, PDF is allowed to have jumps but no impulses. CDFs can have jumps. So if this f is continuous, then if f is or let us say for differentiable f, then we can write what. So supposing a differentiable f, okay, if you have a differentiable f is given, then how do you get the PDF from this? Then you differentiate. Right, this is the exact opposite of this, and calculus will tell you that these two are okay. But I want to make this little more general, right. I do not want to insist that small capital F should be differentiable. In other words, I want to allow kinks. For example, here, right, mathematics will strictly say, no, this point you cannot differentiate capital F with that. I am saying it is okay, it does not matter, right. You take some, right, we will assume that okay, there is some ambiguity in the exact derivative of that point 0, but it really does not matter as far as probability is concerned, right. So you take either, right, for exactly at 0 you can take either 0 or the value from this side, it is okay, right. So this differentiable we will relax a little bit and say that actually in practice we will do this operation even when we have kinks, right. So that we will try to have the maximum use of, I mean, this equation. Apply also to kinks, right. Okay, just say continuous f. So I am going to say for the purposes of this course, any continuous function can be differentiated. Although mathematicians will scream, I'll say fine, doesn't matter. We will live with some discontinuities. After all, what are they going to? What is the derivative going to be? It's going to be discontinuous. And we've said anyway, small f is allowed to have discontinuities. And at those points of discontinuity, you really can't define the precise value of f, but it doesn't matter, right? And anyway, small f is not a probability. It's only its integral as a probability, and how you define it at the point of discontinuity doesn't change any probability calculation whatsoever. So therefore I am saying that, right, this differentiation idea we will apply, as long as we can find some meaningful derivative at some point, right, either from the left or right, does not matter. So jumps, in other words, we are perfectly okay with jumps in F, we are perfectly okay, right. So if there are jumps in F and you integrate, you will get kinks in. Is the word kink okay? I suppose, right, when I say kink I mean I am talking about a point where the slope changes abruptly, right, like this. So you get kinks in capital F, which is fine, we do not have any problem, but jumps in capital F cannot be differentiated. We will not attempt to differentiate discontinuous CDFs, but no, we will not differentiate, right, no differentiation of in the right in this course, right. I am being very specific. In some other course you may want you right, some other teacher might be quite happy doing it, I am not happy doing it, I am not going to do it. So in other words what I am trying to say is that I will not use a PDF model, right, which requires me to put finite probability at a specific, right, x in capital omega. Is this clear so far? The small PDF model is perfectly fine as long as you want a smoothly increasing CDF. For all such cases you can think of a PDF. If you want to have a PDF which is smooth in some portion, I mean smoothly increasing some portion, suddenly jumps in some other portion, and then again resumes smooth increase, then a PDF model runs into trouble, right, and by itself you cannot expect a smooth expect any standard PDF to solve that or to be useful in that situation. So it's best to stick to the CDF and not, right, not invoke things like impulses and all that, which are more trouble, which eventually come back and bite you in different ways. Why do impulses bite? Impulses bite because they are not real functions. Impulses bite because you cannot square them. Are you aware that you cannot square an impulse? Its meaning totally undefined. You cannot look at f squared of x if f contains an impulse. So because you can't manipulate them as generally as you can manipulate other functions, right, I prefer not to bring them in. I think it's just to keep the discussion more sane. I think anyway, let me say it's my prerogative and I don't want to bring them in here, that's all, as simple as that. So is this okay everybody so far? So we mean, all I'm again trying to say, we need both. We can't, right, I mean as a concept, maybe in a particular situation we may not need to bring in the capital F anywhere. We might do all the manipulations we want with the small f, which is fine, but don't forget that there is if you ever need it, the capital F is sitting there underlying, which you can always bring in, and this capital F is in some sense is bounded, right, it is a probability. But analytically it turns out, for example, what is the small f corresponding to this capital F? This is a perfectly smooth differentiable function. So for this capital F, what is the small f? What is the small f here? What is it? What is it? Please tell me. So starting with this capital F, we get small f is what? You going to tell me? 1 by pi into, right, what is the domain? So this is a PDF which is defined over the entire real line, right. So and it has non-zero values everywhere in the real line, not just, right, in a portion of it. So for this model to be valid, we are basically saying that the experiment can spit at you, right, any real number from minus infinity to infinity, right. But CDFs are, why do we not use a CDF everywhere? Because it turns out, even though the CDF idea is more general than a PDF, right, the CDF is analytically more painful to deal with. Like for example, it is much nicer to deal with this rather than deal with this. Can be analytically, or I should say they are in general, right, analytically more complicated to specify. When I say more complicated, I mean more cumbersome, right, not complicated in a conceptual sense, they are cumbersome. So maybe all these words, right, we pretty much have to reproduce an entire textbook on the blackboard at this rate, right. You go look at textbooks, you see all these words coming up, they are cumbersome to specify than PDFs. Why? Because you look at this, look at the CDF corresponding to the spinning pointer. How do you specify it? You would say f of x is 0 for minus infinity to 0, and then f of x is some theta x by 2 pi for x to 2 pi, and then 1. You have all these, you have typically what happens is you get a different bunch of cases, case 1, case 2, case 3, case 4, like that, whereas a CDF has fewer cases and you can say 0 elsewhere, things of that sort. So CDFs turns out, sorry, the PDFs are, it turns out are more compactly written and easier to write down and work with compared to CDFs. And you can also have, right, well, we will come to that maybe at a later date, a staircase CDF, but before that I want to, okay, so I think maybe this is enough for today, right. So we have looked at today, what have we done? We have looked at two different ways of assigning probabilities, one with PDF alone, one with CDF, and we have seen that CDF is in some sense more general than PDF, because whatever we can do with the PDF we can also do with the CDF, but the jumps in CDF cannot be matched with anything in a PDF. Just keep that in mind, right, and we will convene next week with the lectures. Last week we looked at so so this is essentially what we did, right, last this discussion. I think we have looked enough at PDFs and CDFs, so I am not going to look at them again. But they are very important, so please don't mislay that portion of the discussion, right. We will be needing it all the time from now on. But just the acronyms, small PDF in small letters is probability density function, CDF in capital letters is this cumulative distribution function. So the D is not the same, in one case it is density, in the other case it is distribution, right. So in general this we talk of probability distributions, so the CDF in some sense is more general because it allows jumps, right, and anyway, so CDF jumps, these jumps cannot, right, not reflected or not capable of what did I want to say here, not generated by, these jumps cannot be generated by PDF, right. By integrating a PDF you cannot get a jump in the CDF, right. That is the basic, so that is a problem we have with PDFs. So there is some sense limited, but as we will see it is not a very strong limitation, right.